rational exponents. So let's look at how rational exponents work. So the number one thing to know about rational exponents is that they are radicals. So if I have a to some fraction, where the numerator is called m and the denominator is called n, that is literally the exact same thing as the nth root of a to the m. Now, which I should also point out is in fact the same as this. It's okay to write it this way too, with the m on the outside. Yeah, so either one of those is fine. This one is typically the way it's written, but I have to be honest, the way I prefer to do it is generally this. And the reason is the following. I like to make things smaller before I make them bigger. So I always think in charts. So I'm gonna think of something, the way I want to explain this is with a chart, the way I'm visualizing things. So if I make things bigger first and then smaller second, or smaller first and then bigger second, it's two different ways of getting to the same thing. However, most of my work takes place in this area. And so I don't want things to be big in the middle. I want them to be small in the middle. So I make them small first so that they're easy to work with, and then make them big only just as I'm finishing, as opposed to making them big and then having to work with a bunch of big stuff by making it smaller to get to the end. It's usually easier to make small stuff bigger than it is to make big stuff smaller. So that's why I prefer to make things smaller before I make them bigger. So although you will almost always see this written that way, I usually do this. I think this is easier. I'll show you why. So for instance, let's say I want to simplify 27 to the 4 thirds. All right, that looks like a bit of a mess, I think, right? That's a largish number to a fractional power. So let's see what we can do about that. I can think of that as 27, the third root of that, to the 4th power. And doing so requires that I find 27 to the 4th power and then take its third root. That sounds terrible. 27 to the 4th is huge. It's like, what would that be? 81,000? Something like that? No, more like 810,000. That is a bigger number than I would like to deal with. So what I'm going to do instead is think of it this way. Third root of 27, which is easy. I'm going to raise that to the 4th power. That's easy. Third root of 27 is 3. So this is 3 to the 4th, which is 81 if you multiply it out. And there you go. Negatives work the same way negative powers always do. You flip things over. So 32 to the negative 2/5, I'm going to think of that as the 5 is the index. So I'm going to think of it as the 5th root of 32, all to the negative 2 power. 5th root of 32, I'll let you work that out, but it's 2. 2 to the 5th is 32. So this is really just 2 to the negative 2, which is 1 over 4. So you can make these fancier and nastier. I will not do that. I promise you that anything, like what I want you to get out of this is the basic idea of how to simplify these. I'm not looking to throw weird, tricky ones where you're going to have to simplify in some strange way. And no. They're going to be like this, where where the root works out nicely and you raise the power. Basically, I want to get you used to this process, and that's as far as I want to go here. Because I'll be honest with you, this is not a super common thing to have to do in general. If you ever have something like this in a practical setting, just jam in a calculator. If you do 32 to the negative 2/5, your calculator will give you the right answer. I'm really using this as a tool to get you to understand what the notation means more than as like a practical thing that's going to come up, every day, just walking down the street, you're going to have to find 32 to the negative 2/5 or something, right? Like, no. So if you get a weird one like this that doesn't work out nicely, calculator. But I just want you to know like where all the pieces go and then how to simplify. How to simplify the nice ones and then the bad ones. That's what calculators are for. All right, so let's do something like this because I want to show you a little bit of a trick. So or I'll show you a little bit of a trick in just a second. But I just want to emphasize here that the powers here are powers. Like they just behave, the regular rules of exponents apply. It's 2/3 is going to go on everything. And what we're going to get here is 8 to the 2/3, which I'll simplify in a second, times 5 to the 10 over 3, 5 to the 10 over 3, a to the 10 over 3, a to the 10 over 3, b to the 14 over 3. And it is totally fine with me if you want to leave these like that. Although I will show you something cool that you can do to put them back in radical form really easily in just a second. But I want to simplify this number, and then I'm just going to leave the a as a to the 10/3 and the b is b to the 14/3. So 8 to the 2/3, that's the same thing as the third root of 8 to the second power. Well, the third root of 8 is 2, so this is 2 to the second, which is 4. So I want to write this whole thing as 4a to the 10/3 b to the 14/3. And go ahead and stop there. Because I can't find a value for a to the 10/3, there's no real reason to simplify it. The power on it is just 10/3. Like that's just what it is, right? I'll show you a neat way we can turn this into radical form in just a second, but this is fine. Like this is a totally fine answer right here. Whoop, what? There it is. Oh, sorry. One more thing I want to show you, and then we'll do that trick I was talking about. If you have multiple radicals with different indices, they can be kind of hard to combine. Like if you leave these as radicals, it's not even clear how you would combine them. But with rational exponents, it's very easy. It just obeys the rules of exponents, so you turn them into exponents. So this is x to the 7/3 times x to the 11 over 6. And when I have like bases, I add the exponents. When I have like bases that I'm multiplying, I add the exponents. So this is going to be x to the 7 over 3 plus 11 over 6, which I'm just going to go off to the side and get a common denominator and add them. Well, my common denominator is 6, so this is 14 over 6 plus 11 over 6, which is 25 over 6. This is x to the 25 over 6. And if you want to put that back in radical form, you could certainly write this as the 6th root of x to the 25th. And then using what we learned last time when we were simplifying radicals, we could simplify this into two pieces. This would be, I'm running out of room here, but the 6th root of x to the 24th times the 6th root of x, which is, I'm going to block this off here. Sorry. Oh man, this is so messy. I apologize. So 6th root of x to the 24th is just x to the 4th. So this is x to the 4th times the 6th root of x. So there's a little bit of jiggling around in there, but I'll be honest with you. I would probably leave it like this. I think that's fine. There's nothing wrong with fractional exponents. I know it seems weird and unfamiliar, and you're probably used to teachers telling you, always turn it into a mixed number or put it back into radical form. There's really honestly no reason to do that. This is fine. If for some reason you're wanting to get practice turning things from one form into another, sure, go ahead. But like as a practical matter, this right here and this are totally the same, and I don't care which one you use. If I care, I will specify like put your answer in radical form or whatever. All right, so let's look at what I can do with something like this, right? So I've got a radical inside a radical, which sounds terrible, but is super easy. So I have the square root of the cube root of x to the 12th. So this is, I'm just going to turn everything into rational exponents. So this is the square root of x to the 12 over 3, which is the square root of x to the 4th, which is x squared. Done. You can also do this if you want to. I could have written this as x to the 12th. Ooh, that's not a 12. 12th to the 1/3, all to the 1/2. That works as well. Remember that 1/3 is the cube root and 1/2 is your square root. And I multiplied all the exponents together. 12 times a third times a half is 2. That works as well. All right. So a cool thing that I'm going to show you about how to simplify something like this. Oh, I actually wanted to write this as the fifth root. Yeah, sorry. I want to write this as the fifth root. One sec. That's the thing I had there is the second step. So if I had like the fifth root of this, so remember we learned how to split this up into a couple of pieces and simplify our radicals, which totally fine. It works perfectly well. I have to be honest with you though, that's not the way I do it. The way I do it in my mind is this, and that is to think of this as x to the 11, y to the 8, z to the 19 to the 1/5, and then turn all these things into fractions. So x to the 11 over 5, y to the 8 over 5, z to the 19 over 5. And I don't leave them like that. I make them mixed numbers. And the reason I make them mixed numbers is this. Okay, so what is that, 3 4/5? It's because I'm thinking of them in this way. I'm thinking of this as x squared, x to the 1/5, y times y to the 3/5, z to the third, z to the 4/5, which is x squared, y, z to the third times the fifth root of x to the 1, y to the 3, z to the 4. So when I'm trying to simplify something like this, and this is a little bit misleading because this isn't exactly what I'm doing in my brain either, but it's equivalent. What I'm really doing is asking myself, how many times does 5 go into 11, and how many are left over? Well, it goes in twice. So I have 2 x's coming out. And there's 1 x left over. That's the thing on the inside. That's the thing that I couldn't simplify. Similarly, how many times does 5 go into 8? It goes in once with 3 left over, right? So 1 3/5, that's the idea. It goes in once with 3 left over. So I pull the 1 out, the one whole y out, and there's 3 left over inside the fifth root. Similarly with z, or 5 goes into 19 3 times with 4 left over. So 3 z's come out and there's 4 left on the inside. So I'm really thinking of these as sort of like mixed numbers. I guess mixed numbers is maybe not the best way to say that. I'm really thinking of it as what's the remainder? Like how many times does it go in and what's the remainder? So it's more like long division, I guess, but it's equivalent to mixed numbers. So either one of those works fine. And I think that's the easiest way to think of this, actually. At least for me, it is. Certainly, it's more systematic to do the split up into two things, and like absolutely, if you're comfortable with that, go ahead and do that. Feel free to try this. Like this is a nice, not shortcut. You're doing the same things, but it's less stiff, is the way I want to think about it. It's less formulaic. It's not so much of a like do this, then this, then this, so much as a look at each variable independently and ask yourself how many go in and how many whole ones can you get outside and how many are left on the inside. Anyway, that's the cool thing I wanted to show you. Mixed numbers, dividing with remainders, and splitting up radicals are all kind of the same thing, actually. And this is the connection between them. Let me go ahead and pause for a second, make sure that I've hit everything I wanted to hit. Yep, that was everything. Okay, I'm going to go ahead and stop the video now, and I will see you guys in the next one.